Hopefully that is just a fancier way of something that we're already doing. Oh, okay. I think if you're, looks to me like if you're here on a, perhaps, depending on what device you're here, you may have different options like Bree. It doesn't give me the option to let you record. So it may be the device that you're using limits what your options are. Okay, is there anybody who wanted permission to record who has not? Does anybody else want permission to record that doesn't, you don't have it? Okay, and Bree, it's your device. I think Hannah's in the same position. It didn't give me the option to give you the option to record. And all right.
Is there a way, are you recording it yourself, Virginia?
No, I'm not.
Okay.
Or, yeah, I gave up that because I had so much trouble doing it last spring that I just was like, I'm never doing that again. I guess that's one of the things I hope to figure out.
Virginia.
Colleagues, yeah.
So I did a little bit of Googling, and it looks like if you're using the mobile Zoom app, you have to have the premium version to record. So you have to pay for it.
Oh, so if you're using the mobile version, like you're on a phone or a
tablet,
I don't know. Jeffrey's on a tablet, and Jeffrey has the option to record.
You must have a desktop version of the app then.
But it's an iPad. But I know what you mean, and I wonder whether the fact that you are, no, you're here with your, yeah. I want to try to translate something from a Zoom technical sheet to you, because you could read the Zoom help and get a more accurate version than what I would try to tell you, right? But I think the Zoom website's really very helpful, you know, with questions and answers. And so I recommend if you have questions about Zoom, that would be the first place to go. I have found it useful answering my questions in the past also. So, all right, well, let's get started. Well, let's get started. Oh, okay, try not to talk too fast. So today's subject, the first thing we're going to talk about is lake formation. You all have the textbook, or the pages are photocopied and posted on the D12 page. So you all have access to the assigned reading in Calf. And you have the study guide, which is primarily reading questions, things you would answer from the reading. And it's my expectation that you read this reading that's assigned for today and attempted to answer the reading questions. So what I'm going to do now is I'm going to start you off with a little discussion question. The first topic we have is glaciers. How do glaciers make lakes? We have glaciers, tectonic, we have a bunch of other ones too, but I want to just start with glaciers. I'm going to put you in some random Zoomy breakout rooms and see if you and the person or people in your group can agree, how do glaciers form lakes? Now, there are multiple different ways. I'm hoping that the most common way is going to be one of the ways that you think of. Okay, so this is kind of a quick question. Wow, so much has changed since I used this 2 hours ago. I know. Well, this is kind of cool. Okay, so there will be 2 or 3 people in a room. Let me make sure that nobody is depending on Jeffrey. Yes, room 5 was going to be hoping Jeffrey would help. Okay, so go to your breakout room, couple of minutes, see if you can agree. How do glaciers make lakes? If you want a note taker who's going to draw a picture, or just a note taker who's going to say some words, that's all you really need. How do glaciers make lakes?
Hello.
Hi.
Okay, so well, I read what we were supposed to read were 1, 4, 6, and 7, right? The one she posted last week.
Yep, I
Yep.
thought
Okay.
so.
Yep.
All right, so that's what I read, and I mean, I saw the processes behind how like or like the different kinds of lake formations, but I didn't see how glaciers specifically do it. I mean, if either of you know.
I mean, glaciers make lakes just by virtue of deforming the land wherever they are. I mean, back in the last ice age, which is where a lot of our lakes formed, the entire like north half of North America was covered in ice. So when that ice retreated, it sort of left divots in the land where lakes formed. That's how the Great Lakes formed, among other millions of other lakes. So
Okay, here, I think I found the part in the chapter too. Advancing continental glaciers scraped the land, pushing rock and earth ahead or transporting it within their mass. In the process, they not only reworked but scoured the landscape. So, glacial drift is what causes it.
Yeah. They also said 4 different ways that lakes are made through glaciers in chapter 6. So, like the development of a lake can be caused by, and then it has 4 different ways. So, an ice barrier, glacial erosion, glacial deposition, and a mixture of glacial activity and non-glacial processes.
Do you know what page that's on?
73.
Oh, here it is. Ice barrier, glacial erosion, glacial deposition, and a mixture of glacial activity, non-glacial. Okay, all right, I see it. Okay, should we write this down or just say it when she calls on us? If she
I think,
calls on us, even.
yeah, I think saying it is fine. I hope she doesn't
Okay.
care that we write the notes.
Okay. All right.
All right, how we doing? Looks like everybody's back. Who wants to give me a quick idea? Now, like I said, there's more than one way that glaciers cause lakes. So we could conceivably have, every group having a different correct answer. I think the first group back in the main room was room 1 with Brianna and Desiree. Did you guys want to, what did you think? How do glaciers cause lakes?
Um, we said that the glaciers during the last glacier retreat melted. They left behind enormous numbers of kettles,
All right, that's good.
which kettle lakes are large and deep. And it was mostly of North America and Eurasia.
Okay, that's good.
Um,
That's good. So they retreated and they left behind kettles.
mhm.
All right, how about Jiang Li, Sam T, and Ju? What did you guys think?
We also could discuss the kettle lakes from glaciers, and the other one that we had was also in the last ice age period when the glaciers were retreating. They basically like erode the land and kind of cut into it to create like ice scour lakes. So
Great.
that's a type of
Kinda
lake.
like
I guess
cutting
kind
in.
of just digging into the land.
Sure, digging into the land, cutting into the land.
Mhm.
All right, did anybody have any other ideas? There are some other ways. All right, well, this is maybe something that the students in this class who are environmental science majors will most likely have taken some kind of geology class. It's part of the foundation, environmental geology or something like that. So they probably, my guess is that many of the environmental science students have kind of a head start on this question. But let's make sure that everybody has an answer. This is frequently misunderstood, even by sort of native Minnesotans, the land of glacier-formed lakes. So I'm gonna draw a diagram on the board and explain to you. So it's important to understand ice, and that at the peak of the last ice age, like 18,000 years ago, here's North America. North America was, I'm gonna be very approximate here, but, ice. And at the peak of the last glaciation, this is like basically all of Canada and parts of the northern tier of states completely covered with ice. And the epicenter of the ice was like here. This is the area where snowfall exceeded snow melt by the greatest amount every year. So year after year after year, snow falling accumulated here, building up like this giant three-dimensional stack of ice. And in fact, here, there was a mile of ice, a mile, 5,000 feet of ice here. Now, that's a lot of ice. And ice is a solid, but it's not a very solid. If you have a big chunk of ice and a heavy weight on top of it, the ice will actually squish out sideways. Now you can do this. You can take an ice cube and put like a stack of bricks on top of it. And if you're patient, the ice cube will actually squish. Okay, I'm not that patient, right? But what we're talking about is thousands of years. And the result is this great big dome of ice here, squished out in all of these different directions. So as the ice was squishing out, sliding across the ground, it kind of like swept all the plants away, scraped the soil away, dragged down through the sand or the gravel beneath that, and even starts, scraping along the bedrock all throughout all of this region. If you were to look at the glacier in side view, a glacier looks like this. This is ice. This is the ground. Now out here, it may actually, in fact, it is too warm for ice to accumulate. This would be like, it snows in the wintertime, but then it melts in the summertime. But back here is where the snow melts, where the snow lands and never melts. So up here is the accumulation zone of ice, up here. And here in the front, this is where the ice is getting squished out forward. This ice is getting pushed forward because of ice accumulating back there. So if you're right here on the ground, whoa, it sucks to be you, because like right here, the ice is just like scraping forward as it's getting squished out, pushed out from behind. But here at the front, here it's actually too warm for ice to accumulate. So what you have here is melting, constantly melting. So this is liquid water. Now, at the peak of the last glaciation, the farthest most extent of the ice was down around Des Moines, Iowa. And so like this could be modern day Des Moines. Here's a big lake with water coming out from the melting glacier. And here's the ice constantly sliding forward and melting. All right, now as the glacier slides along the ground, like I said, first it picked up all the plant material, it mowed down all the trees and stuff, and then it picked up all the soil and dragged the soil along, and then it picks up all the gravel and the sand underneath the soil, and then it even starts scraping away at the bedrock itself. And all of that stuff gets incorporated into the ice. So the ice here at the front of the glacier is full of stuff. It's full of sand and gravel and clay, right? It's full of all of this sort of ground up rock material that it's scraped up off the ground. All of that stuff is mixed up in the ice. And when the ice melts, that stuff is left behind. So you have this sort of constant deposits of sand and gravel and material that's been scraped from farther upstream, so to speak. Now the climate is always different, right? The climate is constantly changing. There's warm years, there's cold years, there's warm decades, there's cold decades, there's warm centuries, there's cold centuries. Even as it's gradually warming up. And so sometimes the nose of the glacier stays in the same place for years and years. Sometimes the nose of the glacier retreats rapidly. Sometimes the nose of the glacier deposits material and then it slides forward again. When a glacier stays at basically the same endpoint for a long period of time, you get a lot of these deposits piled up. And by a lot, I mean like feet, meters, tens of meters, maybe even hundreds of meters, great big piles, huge mountainous piles of sand and silt and gravel left behind. If the glacier retreats rapidly, there might be very little. If it stays in one place, retreats a little bit, you might get a lake in front of it. So the glaciers can create all kinds of features on the surface of the land. And if you go around Minnesota, pretty much a lot of the topography you see is a record of where was the glacier, how long was it there, how long did it stay there melting. Well, sometimes what happens when a glacier retreats, and it's not this like simple, beautiful curve all the time. Sometimes what happens when a glacier retreats is it'll leave this rough landscape. But embedded in this landscape might be, a block of ice. Here was some ice. But then the glacier expands again and covers the ice with more of this gravelly stuff. So like I said, this glacial till, as it's called, could be, tens of meters thick, maybe even 100 meters in places. So sometimes the glaciers melt back and they'll leave icebergs behind, buried in the sand and the gravel. And they may have smoothed the surface off, but then when this melts, the landscape looks like this. Right? So now you've got a depression in the ground. There may be water in it in the beginning, but actually there isn't, because what we're saying is there was ice here, the ice melted, the ice went away, the sand and the gravel fell down, and now you've got a low spot in the landscape. If this is a low spot and it's got gravel all the way around it, it'll rain because it rains every year, and this will fill up with water. That is a kettle. So a kettle is a lake that's created by glaciers breaking apart, leaving chunks of the glacier behind buried. Then the landscape maybe gets smoothed on top of it. Eventually that buried ice melts, and then you get a depression. If you've got a low spot and it's surrounded by higher land, it will fill with water and become a lake. Now, kettles are sort of this number one famous way that lakes are formed. But of course, the landscape as the glacier retreats may be very irregular just to start with, even without any chunks of ice. But just because the glaciers pause here, they retreat, they pause there, they re-advance, they pause here, right? They leave a very irregular landscape. Any of those little depressions could fill with water and become a lake. So that's a way and a half. Like kettles have a name. This other business of the irregular landscape, that's really just about moraines, for example. And the second main thing with the name is gouging, scraping, scouring, or plucking. And that's really all about when the glacier slides forward, does it gouge the earth and dig a depression? This is much, much less common because it's hard to dig a hole, and you have to have some kind of circumstance where only part of the landscape is gouged, right? So this is much more common. They think like Lake Superior, which is a very deep lake, is started older than the last glaciation, that the glaciers, by moving through it, probably deepened it, that it probably existed before, but that the glaciers moving through it deepened it. But this would be in the category of, gouging, scouring, or plucking. If, for example, the glacier is sliding forward, and at the base of the glacier, it has frozen to the rock, and the rock is not strong. then as the glacier slides forward, it might like pull up pieces of the rock, not just like grinding it down a centimeter at a time, but like actually like pluck a whole piece of rock out. Not common. People get excited when they find evidence of that. Okay, so these are the main ways that glaciers have created a lot of lakes, especially in Minnesota. And there are some other ways too, like glaciers damming things or leaving deposits or pulling parts of mountainsides off. But kettles are the number one named cause, the named cause of lakes in Minnesota. It has the greatest lakes associated with it. All right, any questions about how glaciers cause lakes? All right, let me give you your second one, which would be how do rivers cause lakes? There are at least two main ways that rivers cause lakes, and I will show you examples of lakes caused by rivers in Minnesota. But let me send you back into your discussion groups just for 2 minutes. See if you can figure out how do rivers create lakes?
Hello.
Hi.
Yeah, I don't think I see anything about rivers in this chapter. It's chapter 6, right? I'm looking through it again right now.
It'd be 78, 79.
Okay. Let's see.
So it looks like it's just more of,
Oh, it's not on the PDF.
it's not on the PDF, 78 or 79.
Yeah.
Okay.
I wondered when I was reading this stuff last night why she was skipping pages.
Yeah.
Yeah, because it goes up to 75 and then it stops and then it goes to 84.
Okay.
Yeah.
Yeah, and
How do
84 is just chapter 7.
as how do rivers cause lakes? If you have it, I'm still waiting for my book to come in.
Yeah, so it's basically like when you know how rivers change for like shapes a lot. What'll happen is whenever a river decides to shift the way that the water is flowing, then there's a lot of deposition and erosion, and then that deposition and erosion can leave like a body of water. And so that would be an oxbow lake, is when there's like the channel that used to be the river turns into land, basically because the river decides to choose which way it was flowing. Does that make sense?
Yeah, so the river essentially, if the river starts flowing in the same direction as, like, how does the flow change? You say that part again?
Yeah, so if the flow is to, like, you know how you can have like a meandering river? If
Yeah.
your flow of your river was to just change for no reason, basically,
Uh,
there would be like because rivers deposit minerals, there would still be some deposits on the side, so those deposits would fill in that channel, and there might just be a body of water left because there's still this depression in the ground from where that river used to be.
okay, so this oxbow lakes don't happen unless the river changes flow.
Yeah,
Okay,
pretty
so
much.
that's required. Okay. All right.
So yeah, that was one example, but there's also Vizara lakes, but I'm not too sure on how to explain that one well, so.
By the way, Abdul, there's like a PDF of the entire book that just shows up if you Google calf limnology. So just if you were wondering or if you were interested.
All right, looks like we're almost all back. So who would like to tell me, now there's more than one way that rivers cause lakes. There's at least two main ways. So I guess we're looking to see if anybody knows what those are. Let's see, I'm gonna start with, how about room 3, which would be Abdul, Kat, or Keenan. Can you tell me a way that rivers cause lakes?
Yeah, so we talked about the oxbow lakes,
Okay.
and how, like, if there's movement of a river, so if a river is changing the flow of it, then there's a fill of like minerals that go into where the river used to be, and then there's like a body of water that'll still be left there because the channel moved, and so that's how you get an oxbow lake, basically.
All right, that's good. That's good. And I'll draw you a diagram of an oxbow. How about right now? Yeah. So let's say you've got some landscape. Here's a steep hill, and here's a very gentle slope. And so, you know, water runs downhill, right? And where it's steep, the water tends to run fast, and it just goes straight down the hill. But where it's not very steep, like close to flat, the water flows very slowly. And in fact, where it's a shallow slope like this, the water will tend to sort of meander back and forth. So I'm going to draw a bird's eye view of this. Here we've got a river. It's flowing this way. No, it's flowing this way. And it tends to kind of meander like this. I don't know if you've ever seen rivers that do that, or streams. And here's the thing. Whenever there's a corner in a river like this, there tends to be erosion here on the outside of the curve, because the water is flowing the fastest, and it comes around the corner and it erodes here. But on this side of the curve, the water is moving more slowly, and in fact, sediment tends to get deposited here. That's the word deposition. And so what happens over time is that where you've got a little bit of a curve, you tend to have a bigger curve, because it's eroding on this side of the curve and depositing here. So you tend to get wigglier and wigglier and wigglier curves. But then maybe it's a snowmelt event in the mountains, and there's, in the springtime, a big flush of water. Or maybe there's just a heavy rainstorm upstream, and so there's a big flush of water down the river. Well, if there's a big flush of water down the river so that the river rises in its banks, you know, what do you think is going to happen at a place like here? The river will cut the bank and jump, right? It'll cut a new channel, cutting all this off entirely. And this water may continue to flow, you know, this heavy flow of water, right? And it may jump another place. Well, when it cuts the banks like this, this loop over here no longer has water flowing through it. And this loop over here becomes an oxbow lake. So you see oxbow lakes, places where the landscape is pretty close to flat, so the water is not moving very rapidly, but there's enough water that it keeps eroding the banks and making a wigglier and wigglier river. So I'll show you some. There are a fair number of oxbow lakes in Minnesota, especially in the Mississippi, up north of the Twin Cities, kind of in the Anoka Sand Plain and up into the peatland area, Aiken County, up into southern Itasca County. There are also oxbow lakes and other types of cutoffs along the Mississippi River down in the southeastern part of the state along the bluffs. Although they don't tend to be this sort of vigorous bow shape, they're more like a backwater cutoff. They're often small, too small to count as a true lake, or maybe just not noteworthy enough to be given a lake name. But there are a lot if you look at them on air photos. So I'll show you that. Now, what's the other way? The other way that lakes in Minnesota are made by glaciers. Anybody know another way?
There was blocked valley lakes.
Yeah. Yeah. So this might be, let's say that you have a river. Let's see, we're going to do our bird's eye view here. Here's our river, right? It's flowing down like this. You see that? And this is like, you know, the Mississippi River or the St. Croix River. And then there's another river that comes in from the side, you know, a tributary, right? Well, if it's pretty high elevation here, so this tributary is flowing really fast. Fast flowing water carries more sediment without going into the physics of that. Fast flowing river, carrying a lot of sediment, enters a great big slow moving river. What happens to all that sediment? Well, an awful lot of that sediment, I'm showing a lot of mud, I'm showing, you know, sand, right? It's a fast enough moving river that it's carrying sand. But when it hits this big slow moving river, the water slows down and the sand gets deposited. And what do you get? You get a delta. And if this river is carrying enough sediment, this delta might be so big that it actually dams the river. Now, it's not going to like necessarily dam it entirely, stopping all water, but maybe it's raising the level of this land here, which causes this water to back up. And maybe instead of a smooth flowing river here, essentially what you get is, you know, something like a lake. Now, there are lots of lakes in the Minnesota River called pools that are created by dams, the Army Corps of Engineer dams, right? And the purpose of which was to slow the water flow to eliminate rapids. If you built a dam here, you would expect this to become like a lake, like a reservoir. So this is really just a natural way in which dams are created, but we don't call it a reservoir because, you know, people didn't create it. This river did, the Chippewa and the Mississippi. Anybody happen to know the name of this lake that's created by the Delta Dam of the Chippewa River from Wisconsin, Minnesota? Anybody happen to know what lake this is?
Is it Lake Pepin?
It's Lake Pepin. That's right. That's Lake Pepin. Yeah. All right, so that's two important ways that rivers cause lakes. And I think I've also explained by mentioning dams, the major way the humans create lakes is by damming things. Let me just explain three others kind of quickly, and then I want to show you some pictures. All right, so those are two ways that rivers make lakes. There are also solution or karst lakes. And here it is. If you've got limestone, you can see that's limestone there. And you get water trickling in from the rain. It tends to dissolve the limestone and then flow, you know, as it flows along. And you may end up having places where there's been so much dissolving of limestone that it's all sort of porous. There are cavities and caves under the ground. And what you end up with sometimes is just some sort of collapse. And that could conceivably fill with water and be a lake. And this would be called a sinkhole. Now, we don't have any sinkhole lakes that I know of in Minnesota, but I'm going to show you some candidates. In Florida, this is the #1 cause of lakes. Florida, if you can picture the Florida panhandle, it's basically flat with some big shallow lakes in it. Not the panhandle, but the peninsula of Florida is basically a peninsula of limestone. It's only, you know, a few meters, 10 meters, whatever, above sea level. And the limestone that is most of Florida has been exposed for hundreds of thousands of years. And there's a lot of this kind of subterranean erosion that has gone on, leading to collapses of the surface and the creation of lakes. So, you know, the Florida Everglades, you want to think of that. And so these are called karst lakes or limestone solution. And karst is a place in Italy where this type of landscape is really, really common, and it got named for that part of Italy. So people often call this karst lakes or a karst landscape. Now, another way that lakes are formed is by volcanoes. And again, you know, volcanoes could create lakes in more than one way, but the famous way that volcanoes create lakes is, let's say you've got a volcano, you know, it erupts, and then what you got is a crater. This is our volcano here. Here's the volcanic eruption. You can see that. Yeah, volcanic eruption, boom, you know, and then maybe the magma drains away, or so much of it has been exploded, whatever, not to go into detail, but what it leaves behind is some kind of crater. This could be extremely deep, in fact. But if the rain falls, the depression will fill, and you end up with a lake. These lakes are pretty special, and sometimes they are very, very deep. Often they have very, very clear water because they have just the tiniest of watersheds. So there is very little nutrient input to this lake. Only what's going to come in the rain and erode from, you know, the tiny little bit of land that is in the watershed, right? If rain falls here, it's going to wash away. It's only if the rain falls right here that it's going to get into the lake. So there's very little source of nitrogen or phosphorus or, you know, any of the other necessary nutrients for lakes. So lakes in volcanic craters are often very, very clear water because there's no algae, there's nothing living in it, or very little. And sometimes they're very, very deep. So this is the #1 way that lakes are caused by volcanoes, craters. You know, of course, the ash or the ash flow down the side of the mountain could dam a river and create a lake that way, right? There's other ways, but that's #1. And then the final way that I want to talk about would be tectonics. Tectonics is the surface of the earth is these hard plates that are kind of floating on magma, sort of, and they could come together and push up and found mountains, or the plates could separate and part of the ground fall, right? Part of the ground could fall, and then now you've got a depression. So let's say that you got a couple of tectonic plates. These are all plates here. There's another plate here. And if these plates push together, you could have a mountain form. But if these plates move apart, this one might fall. Right, I'm showing this one in the middle. So if these two move apart, this one might actually fall. Now you've got a depression in between two plates, tectonic plates. This is called a graben, and the oldest, deepest lakes on Earth are tectonic in origin of this basic type. So Lake Baikal in Siberia, which is basically, you could think of this as being like, Russia and China moving away from each other, and Mongolia falling. It's not actually all of Mongolia. Mongolia would be right here anyways. But like China and Siberia moving apart, and Lake Baikal right in between falling. It's a extremely deep lake, millions of years old, a couple of kilometers deep. I mean, it's amazing, amazingly deep. And then, of course, humans create lakes. The number one way that humans create lakes is by damming things, damming rivers, damming streams. The number two way that humans create lakes is by digging them. Whether they dig a little farm pond or a swimming pool, those are pretty small. Or mine pits. An open pit mine where people have dug down into the earth, with not people, individuals with shovels anymore, but like giant bulldozers and machines. Like if you dig a great big pit in the ground, you have to constantly pump the water out or it will fill in with groundwater. And the deepest lake entirely within the state of Minnesota is actually an old mine pit that has filled with water. Okay, well, here what I've done is I've explained the ways that lakes are formed. Now I'm going to show you some pictures. And of course, you have an explanation of these in some different words with some different emphasis from Professor Kalf. So what I'm going to do now is go out to the PowerPoint. Uh-oh. Make sure I can find my PowerPoint here. And okay. Oh, this is a beautiful PowerPoint, so just I gotta find it. Here, where'd it go? Spent far too much time creating this PowerPoint yesterday. Because you know how it is sometimes. Okay. All right. How's that look? Oh, so far so good. Okay, so what I got here is just some examples for you. And these are the different ways, the main ways that lakes are formed. There's a lot more, actually, with a few lakes caused by this or that or the other thing. These are the main lakes that examples that I have explained. And now I'm going to show you some examples of all of them, I believe. All right, here's just a nice picture showing the extent of the last, at the last glacial maximum about 18,000 years ago. Here's a better drawing of North America And here you can see Minnesota and the extent. And then here is the Des Moines lobe, as it's called, and it's scraped down this way. There was an earlier lobe that came this way and that way, and you can tell where the lobe came from by the chemistry of the rocks the gravel that it leaves behind. So, I mean, you could be a geologist if you wanted and learn all that. Okay, well, I think I've explained the formation of kettle lakes, and I would say that, you know, like here's just Minnesota, here is the Twin Cities, here's Minneapolis over here, here is St. Paul over here, Roseville, Vadnais Heights, right? I hope you can see that. Woodbury's over here, right? And all of these, almost everything you see is a glacial lake. I think that, you know, Pig's Eye is going to be a river formed lake, but all of these lakes, and I would say almost all of these are probably best described or typically described as kettle lakes. But they're all glacial in origin, and there's no point in listing them because you'd be listing like 12,000 lakes. Well, what about ice scouring or plucking? Well, one of the lakes that I worked on years ago is called Big Watab Lake. It's just past St. Cloud. It's actually quite close to Collegeville, if anybody knows Stearns County at all. And Big Watab is extremely deep. I don't know if you can tell how deep that is. It's like 120 feet deep. It's very deep, and which is the reason we were working on it. And it is said that the reason it was so deep is because of plucking. And the way that the evidence for that in particular is that, well, okay, it's really deep, and so they want to figure, you want to have an explanation for why it's that deep. On the south shore here, no, down here on this peninsula here, there is rock up on the peninsula that is Cretaceous, not Holocene, not Pleistocene, Cretaceous. Meaning, so on top of this sort of modern rock, modern sediment, is a pile of really, really old rock. And this was taken to be evidence that the glaciers sliding down this way had scraped down through everything, had frozen to the rock at the bottom, and then sliding forward had pulled it up and deposited it on this hillside here. So this was taken as potentially an example of a lake that was at least deepened by glacial plucking, which belongs to the larger category of ice scour or ice gouge kind of lakes. Not many examples. Many of them are kind of debatable as to whether scouring or plucking was really a role in Minnesota. Lake Superior, as I think I mentioned, is almost certainly as deep as it is. It has been there for multiple glaciations. It has survived as a deep lake through multiple glaciations. And part of what has happened is the glaciers have scraped it as they've gone through it. So it's Lake Superior is also thought to be at least partially a product of ice scouring, ice gouging. Riverine lakes, here's a picture of, this is just north of Big Sandy Lake and Savannah Portage State Park, west of Duluth. And here's the Mississippi River going through a very, very flat landscape. And I think here you can see lots of these ribbons, these bows of the lake, and places where the river has bowed so far that it has cut through. Right there is here. Here's another one that used to be a big bow, but it cut through. So here we have some oxbow lakes in existence or being formed. I think you can see these over here. Yeah. And you could just go on Recreation Compass or Land View on the DNR or even Google Earth or whatever and follow the Mississippi River north and see lots of these as they go along. So these would be examples of riverine lakes, oxbow cutoff type lakes. Here's Lake Pepin that we mentioned earlier. This is the Mississippi River going down here. Here's the Chippewa River coming in. I don't know if you can tell, but this is a pretty steep landscape here, as you can tell by the stream dissection of the highlands here. Carries a lot of sediment, a lot of debris eroded off the hillsides, deposited here. We got a great big delta formed, blocking the river channel, creating Lake Pepin. Now I'm kind of on a search personally to find a sinkhole lake in Minnesota, which I'm not pursuing extremely actively, except I did go down to Fillmore County, which is one of the, I think, 5 counties in Minnesota that have no natural lakes. Typically 4 are named, but I think that Fillmore is accidentally off that list because I don't think there are any lakes in Fillmore County. There are no natural lakes that I can find in Fillmore County. And Mower County, which is on the list, I think the Eastside Lake in Austin, home of Spam, I think that's a natural lake. It's got a dam on it, but I think, so anyways. This is Fillmore County. It's down in the southeast corner of the state, not next to the Mississippi River, but 1 county in. And what you're looking at is, this is the tiny town of Wyckoff. And then over here, off the screen to the right is Spring, what's it called? Spring City? Some not very exciting name. And you can drive along this road and you look out over the flat farm fields and you see these weird little islands of treetops. Like you look out and you see like the tops of trees in these little pockets. And these are all sinkholes. Underlying this very flat landscape with a very thin layer of glacial till, under this is very flat limestone, and it's just riddled with caves and subterranean channels and a whole lot of these sinkholes. Now, most of these sinkholes are far too small to be a lake, and most of these sinkholes are all connected to the subterranean drainage system, so they don't hold water. And that's a problem in this part of the state, that, when farm chemicals are spread on the fields, whether that's fertilizer or pesticides, that gets down into the drinking water very easily. And that's a real problem that this particular part of the state has. And it's been in the news when somebody wants to build a great big hog farm. And this is exactly where you don't want giant pools of hog manure, right, sitting around, because it'll get into the groundwater and the people, it's very sparsely inhabited. People drink well water. Anyways, I still hope that I will find one of these that holds water and is big enough to classify as a lake. I haven't found one yet. There is a sinkhole in Minneapolis. Does anybody happen to know where it is? Is anybody from Minneapolis? Did you know that there was a sinkhole in Minneapolis? Well, I'm not 100% sure it is, but I'm pretty sure that the Seven Oaks Oval here in South Minneapolis, so this is Longfellow, here's Lake Street, this is Lake Street, Minnehaha Falls is down below the screen on the bottom of the screen, below the screen. Here's the Mississippi River. Here's St. Paul over here, St. Thomas, Hidden Falls, and so on. This oval here is actually a very deep depression in the ground. And this is all underlaid by limestone. This is this limestone, sandstone stuff that causes all these, makes Minneapolis flat, in short. And then here's the cliff, with the river. So anyways, this is extremely deep. I don't know if you can tell that these are treetops, and the treetops are like at ankle height when you're on the sidewalk next to it. So I'm pretty sure this is a sinkhole, but so far as I know, it doesn't hold water. If it did, it would be the only karst lake in Minnesota that I know of. Now, I do know a karst lake in Minnesota, despite what I just said. I do know of one. It's too small to be counted as a lake. You know, to be counted as a lake, it has to be 10 acres or 4 hectares. So this is too small. Plus, it's underground. So is it a lake? You go down to Forestville Mystery Caves State Park, Fillmore County. In the Mystery Cave part, here in Mystery Cave is a lake. It's a lake. Okay, it's a pond. It's too small to be a lake, but it's caused by limestone dissolution. It's got the right formation. It's got water in it. Its only problem is that it's too small and it's underground. So is it really a lake? Yeah. So you should go there. Very cool. Let's see, what were our other ones? Tectonic, volcanic, and human. Okay, so here we have Lake Baikal seen from the space station. This is a NASA picture. Here's Lake Baikal. I don't know if you can tell, this thing's really big. And like I said, it's like 2 kilometers deep, like a kilometer of water and a kilometer of sediment, because it's a couple of million years old. So there's a tectonic lake. This is caused by, you know, plates separating and a part of the earth just falling, subsiding. Very cool lake. It has endemic species that live nowhere else on earth, things that have evolved there because it's so old and so unique. It's got seals, freshwater sea lions. Yeah, very cool, like Baikal. Then there are the African Rift Lakes, right? Lake Victoria, Tanganyika, and Malawi, the one that kind of looks like a copepod. No, it looks like a rotifer. Malawi. So these are African lakes. We got plates, a couple of different plates here moving in different directions. This is actually kind of a dome of land, which is why it's sort of a round shape. And then at the edges of the plates, you've got these very deep, very old lakes. Some of the deepest, oldest lakes on Earth. And then volcanic lakes, we're going to return to this area here, Cameroon, in a moment, where there's a bunch of volcanic mountains in this area here. But first we have to go to Oregon. Crater Lake National Park in Oregon. This is not the most spectacular picture of this lake. I mean, can you imagine even more spectacular? But this is Crater Lake, extremely deep, clear water. We're gonna look at some data from Crater Lake in a little bit. It's got a little dome over here near the west shore, but I think you can see this has got a really small watershed, right? If rain is gonna end up in this lake, it's either gotta fall on the lake itself or on this very narrow band of shoreline. And that means there's very little area from which nutrients will be released into the water. So the very, very low nutrient concentration, very, very oligotrophic, very clear water. So that's Crater Lake, Oregon. This is Lake Nyos in Cameroon. It's one of a couple of volcanic lakes on this volcanic massif structure. It's really famous for having exploded and killed a large number of people somewhat mysteriously. And the problem was carbon dioxide. So this is a very deep lake. It's so deep it doesn't mix top to bottom. It doesn't have a very large surface area compared to how deep it is. And so the bottom water never mixes. And it's so deep that the pressure is so high that the carbon dioxide is dissolved in the water. And the problem was when something disturbed it so much that some of this bottom water with carbon dioxide dissolved in it got lifted up high enough that it was low enough pressure that the CO2 came out of solution, formed bubbles. Of course, bubbles rise. And then this caused this circulation, which caused more of the deep water to come up, which caused more of the CO2 to form bubbles, and just catastrophically degassed. Gas that was dissolved in the water, carbon dioxide, came out of solution, filled up the basin, flowed down the hill, killed a whole lot of people and animals, and it was pretty tragic. And there is a solution in place to prevent that from happening again, which we will talk about later in the semester. And this is not only a volcanic lake, but also meromictic, because it is so deep. And in fact, the African Rift lakes, Tanganyika and Malawi, are also meromictic, not mixing all the way to the bottom. And then you got ponds, human created lakes. I know this might not look like a very exciting lake to you, but this has a deep personal connection to me. This is the tiny town of New Bremen in upstate New York, near the Adirondack Mountains, kind of close to Kingston or Gananoque, Ontario. This is a mill pond. This is Crystal Creek. Crystal Creek is dammed right here. There's a dam. And the reason it is dammed because that's a mill, a water power mill, 100 plus years old. And that these people are cutting ice. This is the New Bremen Volunteer Fire Department that cuts ice from the lake every year that they use in the summer on the farmers, whatever they call it, the firemen's field days. And this mill back here, see that building there? Yeah, that's my dad's. Yeah, that's my dad's mill. So I have a long affection for ice cutting and mill ponds. And here's the bridge. And I could show you the toe I broke jumping off the bridge, but I don't really think you want to see that. Anyways, so damming creeks, damming rivers is a big way that humans make things that are lakes or lake-like, in which case they might be called a pond or a reservoir, technically. Of course, not all ponds or reservoirs are small. There are also really big ones. Here is Lake Mead. This is Lake Mead. I don't know if you can see this. I'm not sure you can really get a sense of the scope of this thing. This thing holds 40 cubic kilometers of water. That's how much water there is in here. Now this giant lake here, isn't it gorgeous? This giant lake here is a reservoir, and you can in fact see on this slope here, you see that light colored band. This is showing you the difference between the current water level and the high water level. Lake Mead is a damming of the Colorado River, and the purpose is to store the water to be used for agriculture and drinking water downstream, primarily in California, Southern California. So this is a reservoir created for flood control and water regulation. And you might have heard of the dam that created this lake. It's a famous dam. Anybody happen to know the name of the dam that creates Lake Mead?
Is it the Hoover Dam?
It is the Hoover Dam. It is the dam, yes, it is the dam responsible for Las Vegas. Here is the Hoover Dam, seen from sky. This thing's huge. You drive across it. It's got like 2 lanes of traffic. I was over there last spring. It's a lot harder to visit than it used to be, right, since 9/11. But anyways, here's a freeway. This is Interstate I-10, I-10. And then you can go down, drive across the dam. You can park here, walk around. There's a visitor center over here, museum, stuff like that. This thing, you can't believe how big this dam is. This dam is big. It's really impressive. And the electricity generated by this dam created Las Vegas, the home of the neon light. Yeah. Anyways, pretty impressive. But it's, it's a reservoir. It's a man-made dam. And I think that's my last example. No, and then I got the summary here. Just to summarize, right, we started out by talking about Ramsey and Hennepin County. That's right here. I showed you Big Watad Lake, which was in Stearns County, about here. If you can see my mouse, yes, there's Stearns County. For the riverine dams, I was showing you the Mississippi River in Aiken County up here. And then I showed you Lake Pepin, which is Winona County, which I think is this one right here. You can almost see it, it's blue, right here. This is Fillmore County right here. This is the county, this is What's-it County, Olmsted County that has Rochester in it, which also has no natural lakes. Here's Mower County, which they say has no natural lakes, and it might be true. Those are the three. You know, if you're right next to the river, there's riverine lakes. But if you're in here, it's karst. It was not covered by the last glacier. There's no glacial lakes in here. There also aren't any over here in Pipestone and Rock County down here because the glaciers came down like this. You know, I couldn't think of any tectonic lakes in Minnesota unless you, I mean, I suppose ultimately Lake Superior is tectonic in origin. I'm a little confused about how old it is and where it was in the very beginning. So I didn't use that as an example. We don't have any volcanic lakes that I know of, and we have far too many anthropogenic ones to even mention. And then there's a bunch of sources for these. All right, that is my explanation of the formation of lakes, the mechanisms, and some examples from Minnesota. Do you have any questions or comments? That was a whole lot of lecturing. So I forgive you if your mind wandered. Any questions or comments? All right, what I'm proposing that we do now is we're going to take our, it's a little early, but I think it's a good time. We'll take our 10-minute halftime break. And then when we come back, it's not going to be a lot of lecturing. I'm going to give you some explanation of how to calculate things and then give you some examples to practice calculating them about lake morphometry, you know, area, shore length development factor, you know, that kind of stuff. Questions, comments? Ready for a break? If you're ready for a break, you could just put up your out of office sign. If you have a question, raise your hand. Check my chat here. All right, hearing none, 10-minute break. All right, well, let's get started. All right, so we're going to talk about lake morphometry. That's to say the measuring of lakes, measuring of the physical dimensions of lakes. And I'm sorry to say, but limnologists use a lot of different units. So you need to be able to convert from one set of units to another, from one unit to another unit. Now, I know you've done unit conversion probably in multiple classes before. Certainly you have in chemistry, probably also in physics. So this is not the first time you've encountered this. You've probably done this before. What I would like, however, is if I can push you a little bit farther so that you actually understand what you're doing when you're converting units. And I think that's often the way things are, right? First you memorize it, then you use it, and then at some point you actually start to understand it. So I'm hoping that this will be a little bit of review of how to do it, but also push you towards understanding what you're doing. Okay, so what I mean by that is conversion factors. I know this is all going to sound familiar, right? Hopefully. So here's the deal. Conversion factor is what you multiply by to convert the units. So let's say that we're trying to convert between feet and inches, just to start with something that you totally understand. Totally, right? So 1 foot is equal to 12 inches. Everybody knows that. I'm assuming 1 foot equals 12 inches. If I showed you a ruler, which ironically I don't have one right here, but if I showed you a ruler and I said, this is 12 inches long, and I showed you another ruler, I said, this is 1 foot long, you would be like, they're the same length, right? For every one of these rulers, exactly the same length as that ruler, a 1-to-1, exactly the same. Same length, with different units. So let's say that we have 3 feet and we want to convert that to inches. We take 3 feet and we multiply it by a conversion factor. Now, a conversion factor is a term whose value is 1. If you were going to multiply by something bigger than 1, you're going to end up with a product that's bigger than what you started with. We don't want that. We want exactly the same length, but in different units. We don't want it to be bigger. We just want it to be different units. If we multiply it by something that's equal to 1, then we don't change its length. We're only changing its units. We're not changing its length. We're not making it bigger. We're not making it smaller. We're just changing the units. So the conversion factor must equal 1. Well, 12 inches is the same length as 1 foot. So if we have a fraction that is 12 inches divided by 1 foot, 12 inches is exactly the same length as 1 foot. 1 foot is the same length as 12 inches. So this fraction is equal to 1. It is a unitless number because it has no measurement. It's just the ratio of 2 equal things. So this is equal to 1. So we're going to take 3 feet. We're going to multiply it by something whose magnitude is 1, but it looks different because it's written with different units. So 3 feet times 12 inches over 1 foot. The units here are going to cancel, and we're going to be left with 3 times 12 over 1 inches. In other words, 36 inches. So this here is called a conversion factor. It's a factor because you multiply by it, right? Factor, product, right? So if the terms in a multiplication are called factors, so that's a factor. And it's the factor that you use to convert units. So this is a conversion factor. So what I want you to do is, I want you to tell me what the conversion factor is for each of these sets of units. So 1 acre is equal to 0.4047 hectares. And a hectare is an area that is 100 meters by 100 meters. It's a square, 100 meters on each side. So it's 10 to the 4th square meters, 10,000 square meters. And it's a standard unit of measure for like things that are about, acres in size. 1 mile is 1.61 kilometers. 1 foot, 0.3048 meters. So, well, okay, so I'd like you to give me the conversion factor for each of these. Now you remember a conversion factor is equal to 1. So it doesn't really matter whether you write the conversion factor right side up or upside down here. When you plug it into an equation, you need to orient it upside down or right side up. So you can write it either way. So please calculate and express it as a number, a fraction, with the 2 sets of units. Make some boxes here to put them in. Some lines. Now, on the one hand, this is really obvious and simple, and yet on the other hand, there's something a little mysterious about it. So, you might feel anywhere on that spectrum from it's obvious to this is weird. Yeah. All right, so let's start here. Let's say that we wanted we've got a value in acres, we want to convert it to hectares. So, this lake is 10 acres in size. How many hectares is that? What is this number? What is this going to be? Let's see, who wants to tell me? Hey, Desiree, you got an answer? You're just at the top of my screen.
Is it 1 on the bottom?
So 1 on the bottom.
And then 0.4047.
Yep, on the top. And if we wanted to do backwards, if we wanted to convert from, we've got something in hectares, we want to convert to acres, then you flip it over and it would just be the same thing. So you use it this way if you're converting from acres to hectares, you just flip it over to convert the other way. If somebody gives you a distance in miles, they say that the length of this shoreline is 3 miles. Yeah, let's see, what's my favorite distance? 5 kilometers. Yeah, how many miles is 5 kilometers? Somebody gives you a distance in kilometers. You want to convert that to miles. What is this conversion factor going to be? If you're given kilometers and you want to convert to miles, what goes on the top? Miles or kilometers?
Miles.
Miles, right? And on the bottom goes kilometers. So what number is this? It's kind of obvious, right? 1, because 1 mile is equal to 1.61 kilometers. Okay. Now I know, so, right? So when I say conversion factor, these are conversion factors. When you convert from one set of units to the other, and you should always include units in any calculation, include units at every step of a calculation. Like they don't do that in math class, because in math class, they don't have units, right? And often in physics classes, they don't include units because they think they're doing math, or they think the units are obvious, right? So you don't necessarily get good training in that. But in the real world, you should always include the units at every step. And that prevents you from making mistakes. So you look at your units and then you make sure you've got your conversion factor. It's either going to be this way or it's going to be, upside down. You want the units to cancel. And that tells you which way to orient it. Yes, Hannah.
I just switched to a MacBook and I'm able to record now. I just need permission.
Oh, hey. I'm so happy for you, Hannah.
Finally.
And remember, you can borrow, I believe you can borrow a laptop from the university. Just want to tell that to everybody else too, because, they're powerful. Yeah, there we go. All right. So that when I say conversion factor, that's what I mean. Actually, I don't actually, if I say, what's the conversion factor, you could write it right side up or upside down if there's no equation that tells you what your start, you know what I mean? Okay, maybe that wasn't clear. Let's go to an example here. Oh, here we go. Oops. So much to do. So much technology. Very exciting. Here we go. All right. All right, we're going to work with lake maps this week. Here is a lake. This is a map. This lake map comes from the DNR Lake Finder. Lakefinder. Actually, I don't know what the full URL is, but you can just Google DNR Lake Finder. You can put in the name of any lake in Minnesota and you can track it down. Now, I copied and pasted this information from the Lake Finder. And first of all, you're going to find the name of the lake. Now, this lake is the lake formerly known as Calhoun, Bde-Makaska, which to me is redundant because Bde means lake. So this is Lake Makaska Lake. But then Mille Lacs is Mille Lacs Lake. So, okay. It is ID number 27003-100. Its county is Hennepin. For any lake you want in Minnesota that has a record in the DNR database, it's going to have a lake name, a lake ID number, and a county listed. This is a little bit actually duplicative or redundant. Hennepin County is county number 27. So this is county 27. This is lake 31. And the last two digits are, if the lake has multiple bays to it, like a North Bay and a South Bay or an East Bay or a Middle Bay or whatever, the different bays or subparts of the lake will get a suffix here, like 01, 02, 03. Makaska is just basically a pretty round big lake. It's got no bays whatsoever. The whole thing is just 00. So this is Lake 31 in Hennepin County. Okay, so anytime you do a lab on a lake, obviously you would include the county, the lake name, the county, and if it's in Minnesota anyways, the ID number of the lake. And then that's clear which lake you're talking about. Round Lake, for example, there's a lot of round lakes in Minnesota. I don't know how many there are, maybe 100. I wouldn't be surprised if there were 100 round lakes in Minnesota, because there are 3 in Ramsey County alone. 3 round lakes in Ramsey County. Yeah, so you really need to include the ID number in order to be specific about what lake it is. Now, Como, I think there's only 1 Como lake in the state of Minnesota. Phelan, I think there's only 1 in the state of Minnesota. But, you know, a lot of lakes, there's more than 1 lake with that name. Okay, so what is it that we want to know when we talk about the dimensions of the lake, the morphometry of the lake? What are the important dimensions? Well, here, Makaska is a great example. It has an area, which you could get by measuring the area of the lake. It has a shore length. I'm going to skip this one. It has a shore length. That is the length of going all the way around the outside of the lake. And you could measure that with a little device. You know, they have these wheelie-dealy things that you can use for that. If you have a paper map, you can take a string and just lay the string around the outside and then measure the string on a ruler. That's like the olden days, right? The low-tech way, like you're in the field. You know, just take a string on the map and then measure the string. Of course, now what you could do is, you know, what I would do if I had to do this is I would download this map, I would upload it into ImageJ, you know, and use ImageJ to measure it. So there's all sorts of online things you can do. But that would be the shore length. Now, we're going to skip mean depth for a moment because the mean depth is the average depth of the lake. Now, this is a bathymetric map. Bathymetric. And a bathymetric map shows you the depth at all of the different locations within the lake. It's a little hard to read this. It's so tiny here. I think that's 70. And I think this is 60 here. So in between this line and this line, this whole area in here is in between 60 and 70 feet deep. So you can see that it's pretty steep near the shore. You go just a short distance and the depth of the lake changes a lot. That means it's steep. Out here, it's pretty flat. You can go a long distance and the lake depth doesn't really change that much. So it looks kind of like there's a steep area near the shore, kind of a flat area, a gentle slope. Here it's going from, if I'm reading this correctly, 40 feet, 50 feet, 60 feet. So it's gradually getting deeper. And then this whole area is in between 50 and 60. Now the maximum depth of the lake is often, you know, a little place, and it's just kind of like a deep hole, they might call it. Anything inside this ring is 80 feet deep or deeper. Anything inside this ring is 80. Anything, because I can read that as 80. So this must be where it's 82, I think, these 2 little spots. And here it says maximum depth, 82 feet. How do you figure out what the average depth of a lake is? It's a little, we're not going to actually do, you can do it, but there's different ways to do it. And basically it involves finding out how much of the area of the lake has that depth. So the entire lake is 0 to 10 meters deep. Only the area that's beyond the 10 feet. Only if you're beyond the 10-foot line, then most of the lake includes water that's 10 to 20 meters deep. Most of the lake includes water that's between 20 and 30 meters deep. Only a very small area of the lake includes water that is deeper than 80 feet. This tiny area, this area, this area, those three little circles are the only part of the area of the lake where the lake is more than 80 feet deep. So basically, to calculate the mean depth, you think of the lake as occurring in horizontal slices, and you say, you know, what's the area of the first slice of lake? What's the area of the second? What's the area of the next one? You know, what is the area of the lake that is between 80 and 90? That's how much of the lake is that. Then you can calculate the volume of each of those layers. And then you can add it all together and get the total volume of the lake. Then you take the volume of the lake and divide by the surface area. And that gives you the average depth. So like if you think that through, I think unless you have a lot of trouble with three-dimensional stuff, okay, which is true. Some people have trouble with 3D stuff, but if you think that through, you can see you would calculate the mean depth by first calculating the total volume of the lake, and then you divide the volume by the surface area. It's a little laborious to calculate the total volume, so we're not going to do that. You would just be given the volume. Excuse me. All right. So the first thing we want to do is we want to look at the Makaska and calculate the, convert these units to the other units. And like I said, limnologists have to use both English units, you know, miles, acres, and feet, and they have to use scientific units, meters and hectares and square meters and kilometers. And you have to use both of them because really science is mostly done using the metric system. But you know, engineers and the public tend to use the English system. So you have to be able to use both, and you have to be able to convert between them pretty quickly. So I'm just going to convert between these here on the board right now, and then I'm going to give you a practice to do in some groups. Okay, so you can you can convert these units on your own, or you can watch me do it, whatever you know, whatever makes you happy. So the area for this lake is 419.41 acres. I really like red. I'm going to switch colors here. The conversion factor, to convert that to, what do we want? We want that to be in hectares. So we're going to convert 1 acre is the same as 0.4047 hectares. And that's going to be the area. And then we got the shore length. And the shore length here is 3.15 miles, which I should know without looking, because I have run around this lake and it's almost exactly 5 kilometers. So the conversion factor here is going to have miles on the bottom, kilometers on the top. And then we're going to calculate the, let's see, which one we're going to calculate, the mean depth. Let's just convert the mean depth. $30 feet. I'm going to convert from feet to meters. And we use 1 foot is equal to 13048 meters. Okay, so 419.41 acres times 0.4047 divided by 1 is 169.7 hectares. 3.15 miles times 1.61. 3.15 miles times 1.61 kilometers. 5.07 kilometer. 30 feet times 0.3048 meters per foot is 9.144 meters. All right, so this is what you get, right? Anybody get anything different? Did I make any mistakes standing here? So I just took acres, I multiplied it by my conversion factor with acres on the bottom and hectares on the top. Miles, same thing, mile on the bottom, kilometer on the top, there's my conversion factor. Feet, feet on the bottom, meters on the top, that's what I get. Now, the kind of the rule they use in Minnesota for lakes is it's got to be at least 10 acres, so, or 4 hectares. So is this lake a lake? Yeah, it's like 420 acres. It's far bigger than the minimum. And 170, far bigger than the minimum. All right, yes. Okay, Ju.
Should we remember these conversions, like, for example, like 1 acre equals 0.4047 hectares?
You know, it's a useful thing to remember, but there are a lot of numbers here. You don't need to remember them. I think it's very helpful to remember that there's, you know, a meter is about 3 feet, right? It's useful to remember that 10 acres is about 4. Yes, that 10 acres is about 4 hectares. And that's important because that's, you know, the division between lake or not a lake in Minnesota. So, you know, it's helpful to remember some of these things and have a ballpark sense that a hectare, you know, is, yeah, you know, like maybe twice as big as an acre, you know, kind of a general sense. The actual conversion factor number, you can always look it up, or on an exam, I'll give you a conversion sheet. That's what I would say.
Thank you.
That answers that question. Other questions? All right, one of the things that we want to know about lakes is not just these basic numbers, which are important, right? Bigger lakes are different from smaller lakes. Deeper lakes are different from shallow lakes. Lakes that are very convoluted with lots of bays and points are very different from just a simple circle of a lake. You know, it's important to remember the difference between length, area, and like volume. Those are 3 really important words: length, area, and volume. You know, what that those are separate things. All right. Some of the other things that are very important about the morphometry of the lake are how much of the lake is shallow. A lake might have a deep part, but if most of the lake is shallow, that's really different from a lake that's like all deep. Now, when we talk about shallow versus deep, really the most important thing is whether rooted plants can grow there. And that is the littoral zone. So the littoral zone is where plants can grow rooted to the bottom of the mud. And if there's plants growing rooted in the mud, you know, and they create a bed of plants in the lake, right? They support lots of algae up in the light. Now, most things in the lake don't eat plants, but the stuff that grows on the plants, the algae, that's the base of the food chain. So the more plants you have in the lake, often the more of everything else you can have. The more zooplankton, the more planktivores, the more piscivores, more of everything. The overall productivity of a lake in terms of like fish production is strongly influenced by how much of the lake is littoral zone. So a lot of what the DNR is interested in is fish production because, well, I mean, people care about fish and, you know, and so on. So they include this very basic information of how much of the lake is littoral zone. Now for Calhoun or Muskoka, right? More than a third, but less, more than a third? What's a quarter of 420 would be 105. So more than a quarter, but less than a third of the lake is littoral zone. More than a quarter, less than a third. And that's probably, you know, one of these lines here is kind of the 15 foot line. 15 foot is generally the easiest way to say, oh, the littoral zone is anything less than 15 feet deep. And if you think about how much of this lake is less than 15, I wouldn't say that was more than a quarter of the lake. No. So the percent of the lake that is littoral zone is an important characteristic. Another characteristic is the shoreline, what's called the shoreline development factor. I guess I should write these two things up here. Okay, so we got those things, we can calculate them. The percent littoral zone is simply the littoral zone area divided by the area total. Well. Okay, so I wrote that on the board and that was not very useful. So actually what I'm going to do is I'm going to try, no, I'm going to stop sharing. I was going to try annotating, but I don't think I can do that neatly. Okay. So the percent littoral zone is simply the area of the littoral zone, capital A sublittoral, right? Versus capital A is the total, you know, the area of the littoral zone divided by the total area. The next most, in fact, the other most important factor that I want you to calculate, and then I'll give you a third one too, is the shoreline development factor. Right, and that is going to be equal to the length of the shoreline of the actual lake divided by the length of the shoreline of a circle of the same area. So it's the area of the lake, sorry, the length of the actual length of the shoreline of the lake divided by the smallest possible shoreline. And that would be the length of the shoreline if the lake was a perfect circle. And you might be like, okay, what's the formula for that? Okay, look, what is the length of the shoreline of a perfect circle? Well, the area of a circle is equal to pi r squared. The circumference of a circle is 2 pi r. And the circumference of the circle is what we're saying, you know, would be the shoreline of a round lake, a perfectly circular lake. Now, if it's a perfectly circular lake, right, the area is equal to pi r squared, and therefore the radius is equal to, so divide both sides by pi, right? And then take the square root of both sides. That's the radius of a circle as a function of its area. I just took a equals pi r squared and rearranged it. I solved it for the radius. This is the radius of a circle expressed as a function of the area. Now I'm going to take this and I'm going to plug it in here because I want to get rid of radius. I want to have the circumference expressed as a function of the area. I want to have the shoreline expressed as a function of the area. So I'm going to take this r here, and I'm going to put it in here in place of this one, 2 pi area divided by pi. Okay, this is the shore length, the smallest possible shore length. It's the length that you would have if the lake was a perfect circle. Now we could simplify this a little bit farther, right? Because pi is inside the square root sign and outside the square root sign. So we can make this a little bit simpler. And what I'm going to remind you is that the square root of pi squared is equal to pi, right? If you've got x squared in here, the square root of x squared is equal to x, right? So we could put the pi in here if we replace pi with the square root of pi squared. So I'm going to move this in here to make this pi squared. And then that's just a whole lot simpler. You're like, it doesn't look simpler. Well, it is simpler because look, we got pi squared over pi. So that means that this and one of those will cancel out. So now we've just got 2 times the square root of a pi. So the shoreline development factor is the length of the shoreline divided by the shortest possible length, the circumference of a circle that has the same area as that lake. In other words, two area times pi. And that's a little times sign. So the shoreline development factor is equal to the length of the lake shoreline divided by 2 times a pi, the square root of a times pi. And that looks like a mysterious function, you know, but it's not really. It's just as I've explained it. Now this is explained in Calc, gives this right here. Oop, right there. Right, so you've seen this. You have already seen this before. This is just an explanation of where that came from. All right, so we could calculate the shoreline development factor by converting from miles to meters, square meters. Did I say that right? We're converting from miles to meters, and then we have to convert the area from acres to square meters, because we need to have both of these in meters, in the same units. And if this is in square meters, we take the square root of it, then this is in meters, and that is in meters, and then the ratio of them is just a number. Right? You can't do that with acres. It's just like a real pain. So you really want to, you can convert acres to square feet, you see, but anyways, we're gonna use the metric system. So you need to convert to meters and square meters, then you can get the shoreline development factor. Okay. Hopefully you got that. So just to practice, oh, I erased those values before, okay. And then the last thing we want to do is fetch. Fetch. Sorry, that's not spelled right. Fetch. And let me show you what fetch is, and fetch is very important. There's a difference between a lake that is round and a lake that is long and skinny. There's a difference between a long skinny lake with a long shoreline and a sort of blobby lake that's got lots of bays and points. They might have the same shoreline development factor, but they're still different from each other in a really important way. Let me show you that factor here. Let's go back to this lake. Here I shall annotate with a line. I want to show you fetch. In this case, if we wanted to talk about the major axis of this oval, or we want to talk about the, what's the right word that I want to use? North-south, that's what I wanted. Oop. We would draw, oh my goodness, we would draw a line, okay, Zoom, you could do that. This is the fetch. This is the north-south fetch. This is the major fetch, or the long axis fetch. And if you were to measure the distance from here to here, then that would be the fetch. Now, how would you do that? On this type of diagram, well, what you do is you would measure this with a, literally measure it with a ruler. You know, how many centimeters long is the lake? And then go down to the key down here and measure this distance here. This is the scale of the map. It is in feet. From here to here is 1,320 feet. So you would make a conversion factor that is, you know, however many centimeters long that is with the ruler. So let's say that it's 2 centimeters, and the 2 centimeters equals 1,320 feet. 1,320 feet. And this is, 2 centimeters on the map equals 1320 in the real world. So on a paper map like this, you would measure, well, not even a paper map, but any kind of map like this, you would measure the distance across the length of the lake in whatever units your ruler is using, like millimeters or centimeters or whatever, and then determine your conversion factor using the map scale. For example, if this is 2 centimeters long, then the conversion factor is 2 centimeters equals, like 2 centimeters on the map, equals 1320 feet in the real world. And then you take your measurement here in centimeters and you use your conversion factor. Now, normally in this class, I have paper maps and we actually measure it in groups right now and do the calculation. I still want you to be able to do this on the exam, so I hope that you can picture doing this. If you were living in an electronic world, if you might have a map like this, and you could be using some kind of software like ImageJ, which could give you a measurement from here to here in pixels or something. And then you measure the length from here to here in pixels, and that's your conversion factor. Now, if you're using GIS software, some kind of geographical information system software, it will be able to, incorporate that. You don't even have to do the converting. Yeah, so we'll have to see how that goes. I'll show you something. So what you're gonna do in lab this week is we're gonna take a lake, round lake, and we're gonna measure it. There are going to be 3 groups of students who arrive at 1 o'clock, and I will start you at 3 different places on the lake. Each group will go from the southernmost, for example, to go all the way the longest part of the lake they can go, like the southernmost place to the north, to straight north, easternmost place to straight west, or vice versa, the westernmost place to straight east, the northernmost place to straight south. Anyways, you'll go across the lake, the 2 different directions, measure the distance. The lake is pretty close to round. So take the average of those 2, and that will give you an average diameter. Each group will then report their average diameter to the class data sheet and the calculated area of the lake. 3 groups will start at 1 o'clock and do this. 3 groups will come at 2:30 and do the same thing. Then we will have 6 data points. Everyone uses all 6 data points to calculate the average area and a confidence interval for the area. Yes, which is a simple thing to calculate. And then the question is, is this lake actually a lake? Is it actually significantly greater than 10 acres, or what we're going to use square meters, 4 hectares? If 4 hectares is, I guess we're going to take this as a positive thing. Are we trying to disprove the DNR, right? So if the lake is significantly less than 4 hectares, based on the average of these 6 data points, it's not a lake, it's a pond. And then, but if the 4 hectare mark is in the confidence interval or below the confidence interval, then it is a lake. Okay, well, that's my verbal explanation. This is written in the lab instructions. The key thing is that you are going to go measure the diameter of this lake twice. one's going north-south and one's going east-west. Every group is going to do that. And then we're going to have 6 measurements of the lake and 6 areas calculated. Each group will calculate the area. Okay. So the concept of fetch is typically taken to mean, what's the length of the lake in its longest direction. And so we can talk about the fetch of the lake in terms of its length and its direction. This lake, it's pretty unambiguous. This looks like the longest cross you could make of the lake, and it's pretty much straight north-south. Sometimes we specify what's the north-south fetch, what's the east-west fetch. And that would mean, even if that wasn't the longest direction, what is it? So this is the north-south fetch, this is the east-west fetch. For this lake, it's pretty obvious. The north-south fetch is the longest fetch. The east-west fetch is perpendicular to that. And this would be you could call this the minor fetch or the perpendicular fetch or the secondary fetch. People don't talk about that very much. Usually they just talk about the major fetch. And that's because if you've got a long, skinny lake and the wind is parallel to the length of the lake, then you're going to get a lot of wind energy from that. If you've got a long, skinny lake, but it's perpendicular to the wind, then there's not that much wind energy going to mix the lake. When the wind blows across, say, Lake Erie, which is a long, skinny lake, when it blows across the lake lengthwise from west to east, wow, it actually piles the water up on the shore, on the Buffalo end of the lake, the New York end of the lake, the east end of the lake. And if the wind ceases, the water sloshes back. It's really kind of spectacular. So fetch is really important with respect to the wind. All right. So I think I've explained everything here and shown you kind of how to do it. What I'm going to do now is I'm going to give you an assignment. What I would like you to do is I'm going to clear my scribbling on here and go to the next one. I'm going to give you a lake and have you calculate it, theoretically. Okay. Here is Como Lake. What I would like you to do is take a screenshot of this, for example. Take a screenshot, and then in your breakout room, and hopefully you can read this on the area there, literal shore length max depth. And what I'd like you to do is see if you can, first of all, convert these to metric, and then calculate the percent literal, the shoreline development factor, and the fetch. These require different skills. The scale is not on this map. Okay, so you can't actually measure the fetch. Okay. Why is the fetch, why is it not on here? Looks like it's behind this whiteness. Okay. So here's Como Lake, area 71.3 acres, literal 68.45, shore length 1.3, maximal depth, which is right here, 15.5 feet. So what I'd like you to do is convert these to metric, calculate the shoreline development factor and the percent literal. All right. I'm just pausing so that, I suggest taking a screenshot or writing these numbers down. And then I'm going to send you into some breakout rooms. They are going to be random, but hopefully a person in each
Chris
group.
Ricard, what's the percent literal formula again? I can't see it.
Wait a minute. A percent literal is simply literal zone area divided by total area.
Ah, okay.
What percent of the lake.
All right.
Yeah. Okay, I guess I have to Where did, oh, very odd. Jeffrey can see it, you can see it, I just can't see it. Okay, we're all good. All right, so what I'm gonna do now is stop sharing and send you into breakout rooms. These are gonna be the same rooms you were in before. If that seems like, so hopefully either Elizabeth or James is, I'm gonna send you guys into room 4 with Breton and Dolly, okay? Just so that we're bigger rooms. Room 4, room 4. Okay, we got 4 rooms with 3 or 4 people in each of them. So hopefully someone in each group has these numbers. Desiree, you're all alone in your room, so I'm gonna send you to room 2. Okay.
Hello.
Hi.
Okay. So the literal area is 96%. She wants us to get the, what are the other ones? The shoreline development factor. Oh, she said we couldn't get the fetch, right?
Right.
So we need to convert those into meters. Is that all else we're supposed to do, or?
Yep, I think so. It's just converting it into scientific.
Okay, so convert those into meters. Area is
Okay, so what do we do first?
I did the literal zone first, the literal area, and
Okay.
I got 96%. And then I, if I recall correctly, I think she just wants us to convert the area, shore length, and maximum depth into meters. And then I think I thought she also mentioned that she wanted the circumference of the lake, if I'm remembering correctly, but I'm not sure. But I don't remember the formula. I don't have that written down.
I don't remember her saying anything about the circumference. So
I could be wrong too.
yeah. I'm not sure though either. So if you want to calculate it, feel free. I'll skip on that one though, because I don't remember the formula either.
Yeah. So, okay, okay, at least we can compare for the area of the lake, I got 288,540 meters, I think. That's what I got.
Okay.
And then 2,784 meters is the shore length. And then 4.724 meters deep for the depth.
Now, are you sure she wanted it all in meters, or did she just want those converted to metric? Like, I'm not 100% clear on that.
I'm pretty sure it's just metric. I don't think it has to be specifically meters.
That's kind of what I was thinking.
Yeah, so I'm just doing metric.
Did she write down the the conversion factors? Do you guys have those? Like the only one I can remember is like 0.4047 what was that, hectares an acre?
Yeah, so for mine, I could also just screen share it for the conversion factors.
Okay, yeah, go ahead.
That'll just be easier for me. Do you see that?
Oh, yep, I do. Let me. Oh.
So does anyone have any questions or anything, or are you guys feeling pretty confident?
I mean, I don't know. I mean, just on this stuff though, the conversion is not a big deal.
Okay.
That's fine. Yeah.
All right. I'm gonna stop screen sharing then if that's okay.
Yeah, that's fine. Go ahead.
Okay.
right, it looks like we're almost, everybody's back. All right, so tell me if you got the same numbers. Now, my numbers might be a little different just because I was looking at two different places, but we started out with an area of 71.8 acres. That converts to 28.8, 28.9 hectares. Literal area, 68.4 acres. That converts to 27.7 hectares. To get the percent literal, you're just going to take the literal divided by the total. Actually, it doesn't matter whether you use acres by acres or hectares by hectares. You should come up with the same thing, which was pretty big, wasn't it? Like 96% or something. What, 68.4 divided by 71.3? So this lake is like 96% literal zone. Is that what you got? Is that a yes? Give me a yes. Yeah, give me a yes at that. Good, because if you got it, that's good. Yay. All right. And then the shore length development factor, right? So the shore length, 1.73 miles. That converts to 2.74 kilometers, which is 2,740 meters. Now the circumference of a circle of that area, if the area of the circle is this, I believe the circumference would be about 1.9 kilometers. I got 1892. Not sure I started with that number. I started with something close to that. Is that what people got? About 1.9 kilometers? About? Okay, I'm not hearing any disagreement. And so then you just take this ratio, 2.74 kilometers divided by 1.89 kilometers, and I think I get about a 1.44 development factor. Which, in other words, it's like 40% longer than the shoreline would be if it was a perfect circle, right? So the shoreline development factor, the smallest possible one, is 1. So this goes from 1 up. The farther above 1 it is, the more different it is from a circle. And this is about 44% longer than the circumference of the circle. And then the maximum depth, 15.5 feet, that converts to 4.7 meters. And then the mean depth was like 7.5 feet. So the mean depth was about half of that. But the mean depth wasn't on that diagram. All right, that all worked. It all makes sense to you. That's kind of the calculation of it.
Could you run through how you calculated the circumference again, if you wouldn't mind just kind of running through the math if you have the time? Or willing to.
The idea with calculating, well,
Like I got the shore length right, I had an error with figuring out my circumference.
Yeah, the circumference, the L of a circle, you do that, you take pi r squared is the area, and 2 pi r is the circumference. You take those two formulas and you combine them, right? Area of a circle is pi r squared. The circumference of a circle is 2 pi r. You combine those two, and you get that the circumference is going to be equal to 2 times the square root of the area times pi. So you take these two, you combine them, and get circumference in terms of area. So you combine those two, and you end up with this. So that's how I did it.
And then when you plugged in the area, you just plugged in the hectare value or the acre. I guess it doesn't really matter at that point.
You got to plug in the area in square meters.
That's it. Okay.
That's the key. And you got to remember that a hectare is equal to 10 to the fourth meters squared. So a hectare is like a square that's 100 meters on each side. You know, it's like two soccer fields side by side, right? 100 meters by 100 meters. That's 1 hectare. So if it's 100 meters by 100 meters, that's 10 to the fourth meters squared.
Yeah, that's where I
And you gotta have it in meters
no.
squared, yeah, because you're coming out with meters. Otherwise, you're gonna have like square roots of hectares. Yeah.
Thank you.
You bet. I think that's a good question. Thank you for asking. All right, so we've done all this, and I think this kind of leads to 2 other questions, which is sort of, well, okay, why is that important, and what are lakes typically like? What are lakes typically like, and why is this important? Like, what do the data show? So I'm going to show you some diagrams from Calf. We are not going to calculate hypsographic curves, but I described it earlier. The hypsographic curve is like this. And this is showing, you know, how much of the lake is at each depth, right? So the maximum area, the whole area of this cartoon is 0. Slightly less than that is 1 meter deep or deeper. Slightly less than that is 2 meters deep or deeper. Here's how much of the lake is 5 meters deep or deeper. Here's how much is 10, and so on. And so you can get kind of a curve showing the area of the lake that it is at each depth. And then you can calculate kind of the volume of each slice of the lake. Like this is 1 slice of the lake, a 5 meter thick slice of the lake near the surface. What's the volume of that? Here's that number. You can add all of these up to get the total volume of the lake. Take that total volume, divide it by the area, and that gives you the mean or average depth. Here is a little cartoon of a hectare, a little square that is 100 meters by 100 meters. So limnologists do hypsographic curves, and then they use that as a way of describing how different lakes are. Like, kind of like, here's the hypsographic curve for Lake Ontario, which is curious, right? Because it's almost a straight line, isn't it? And then it's very deep. Here is a Swedish lake, Vanern, which is much shallower. Oh, it's only 100 meters deep. But you see, it's more of a curvy shape. Then you get something like Lake Chad in Africa, which spans a couple of different countries. And look how shallow it is. And almost all of the lake is very shallow. So especially for big lake limnologists, I think hypsographic curves really tell you a lot about the structure of the lake. What are lakes like typically? What's the relationship between the average depth of a lake and the maximum depth of a lake? You know, you might wonder, I mean, typically, well, I mean, you expect that a lake with a deeper maximum depth would have a deeper average depth, but is that really true? Calf loves that kind of question. Like, is it really true? What do the data show? Here's a bunch of data sets from around the world. So for example, so Evel Gorham was a limnologist at the University of Minnesota. So here was some work he did, and he worked around the world. Anyways, so when he looked at lakes all the way around the world, 71 lakes total in the data sets. The deepest lake in the data set was 1,741 meters deep, which is obviously Lake Baikal. Just in case you wondered, that's Lake Baikal. So 71 lakes around the world, including Lake Baikal. What was the relationship between the mean depth and the maximum depth? Well, if you just take all that data and make a scatter graph and fit a line to it, what's the formula for the line? And that is what this data shows, is the formulas for the line when people graph this. So what we've got here is the maximum depth on this axis, the mean depth. Z is usually used for depth, so I'm going to use Z max versus Z mean. And what they found is if you take a bunch of data lakes, every one of these dots is a lake, and you fit a line to it, and then you say, what's the equation for this line, right? Y equals mx plus b, or in this particular case, the Z average, or I use AVG, the Z average is equal to, in this data set from Gorham, the slope of the line was 0.46 Z max. So we've got Z max as the X variable, Z mean or Z average as the Y, and the slope of the line was 0.46. So in other words, the average depth was really close to half the maximum depth. And when you look at a big data set, right? Just a big data set, and what you see is that, you know, you double the maximum depth and you double the average depth, and the average depth is typically about half, or 46% of the maximum depth. You will see lots of tables like this in this textbook. I draw your attention to them in the reading questions. I want you to learn to read information presented in a table like this. Often it is showing something like the formula for a regression line. Now in this particular example, which maybe I will highlight here. So in this particular one, it's a regression line for Z bar, which is Z average or Z mean, you know, whatever, it has different symbols. That's the formula. You can see the slope of the line is a positive number, 0.46, and that it's simply linear. There's no exponents on the Z max. Now you could look at these other data sets. For example, Gorham's, let me find another one. Let's just pick one at the bottom here, Chow Fraser's. You can see that the coefficient is 0.45, meaning typically the average depth of the lake is 45% of the maximum depth of the lake. But there's also a little bit of an exponent here, 0.94. Now, if there's no exponent shown, the exponent is 1. And honestly, when I look at this, what I see is that two of these data sets, the ones with the two biggest data sets, there's no exponent. And in the ones that do have exponents, most of them are pretty darn close to 1. So I'm thinking this relationship is pretty close to linear. It's pretty close to a straight line. Now, if there's an exponent, like it was squared, you know, it would go up like this. It would curve up if it was a square. If it's less than 1, it's going to flatten out, you know, like more like an asymptote. But to be honest, these exponents are pretty close to 1. So my sense from looking at all of these different studies with different numbers of lakes in them, or with different places in the world, is that it's basically linear relationship. Double the depth of the lake, you're going to get twice the maximum depth or twice the average depth, and that's typical. You do see in different parts of the world a different, you know, is it close to 45%? Here in Scotland, 75%. And what that means is that the average depth in this group of lakes was typically 75% of the maximum depth. These tend to be steep-sided lakes. In Japan, on the other hand, it was only about 42. That's kind of at the other extreme. So there's a lot of information available in a table like this, but you really have to think it through. What do these numbers represent? What are the units? Is this from a graph? What is it saying about the graph? This is the first time we've looked at a table like this, but we will see many more, probably, you know, at least one every week. Okay, so that's the relationship between the average depth of lakes and the maximum depths of lakes in different sets of lakes around the world. Let me see, I need to clear that. Clear all drawings. All right, this diagram just shows what difference does the average depth make to a lake, right? If you look at a bunch of different lakes around the world, excuse me, what effect does the average lake depth have on a lake? On the x-axis, we have the average lake depth, and on the vertical axis, we have productivity. How much productivity? How much photosynthesis? How much production of fish per acre? You know, how much biological production of organic matter? How much growth, right? There's different ways to measure that. One of these lines is chlorophyll A, which is a typical way to quickly measure how much algae is in a lake. One of these is total phosphorus. That's another way to kind of quickly measure the total amount of algae in the lake, because all algae have phosphorus in them. And then the third line, the solid line, is the total fish catch, which is, you know, I think it's like pounds of fish per hectare, or kilograms of fish per hectare or something. And this is a top of the food chain measure of productivity. And what you can see is that as the average depth increases, the productivity of the lake drops rapidly, and then it kind of levels off. So you see the biggest difference in productivity occurring, you know, in the first 10, 20 meters of depth. You get beyond about 20 meters deep for the average depth, and it doesn't really matter beyond that how deep the average depth is. So the most productive lakes have average depths less than 30 meters for sure, more like 10 or 20. And this is productivity per square meter or per hectare or per acre. How about that shore index, that shore development factor, right? There's different versions of the shoreline development factor. This one is calculated by taking the kilometers of shore, just a ratio between kilometers of shoreline to square kilometers of lake, which is not that different from, you know, what we did with shore development factor. Anyways, what you see is that, you know, the more complicated the lake is, the greater the relative shore length is. Relatively speaking, is there a lot of shoreline on this lake or just a little bit, right? Relatively speaking, like for a lake of that size, that's a lot of shoreline. Well, versus for a lake of that size, there's not a lot of shoreline because it's very circular. What you see is the greater the shore index factor, the greater something like the shore development factor, the greater the productivity. And in this case, this is ducks and geese. This is waterfowl. So wildlife people care about the shoreline development factor and fisheries people, and there's a correlation. What about the ratio of pelagic to littoral zone, or which is a different way of looking at the percent littoral zone? If a lake has a lot of littoral zone, the ratio of pelagic to littoral is going to be a really small number, right? It's going to be dominated by littoral zone. If most of the lake is open water, if most of the lake is deep water, then it's going to be over here on the right, dominated by pelagic. And this is just kind of showing how do lakes in the world kind of fall on this kind of scheme of things. How many lakes are there that fit into this category? How many lakes in the world fit in this category? And I think maybe what you can see is that, you know, there's a sharp drop off when you get here. It's really only the really big lakes that are going to be in this group here. Most lakes seem to fall kind of in this category, dominated by the littoral zone, right? 10,000, 100,000 lakes, wait, million lakes, whatever, you know, as you go down. The number of lakes, the greatest number of lakes is going to be these dominated by littoral zone lakes. Okay, so that's kind of like, what are lakes in the world like? And then I was going to conclude, here's Lake Phelan. For lab of this week, here's Lake Phelan. For lab of this week, we are going to this lake here, which is Round Lake. And we're going to meet at the parking lot that's up off the top of the screen there. There's a parking lot up there. If you accidentally go to this parking lot, that's okay, because you'll see us. And in fact, the second time we go to the lake, we will meet at this other parking lot. But this time we're going to meet at this parking lot over here, the one that's closest to Arcade and the stoplight and all of that. Okay, I'm going to stop sharing and wrap it up by saying, oh, I totally missed this topic here. Lost my pacing. Okay, so lab on Thursday, like I said, half of the class, 9 students are going to meet at 1 o'clock. 9 students are going to meet at 2:30. I've written the names of who volunteered for which shift as a note on the D2L page. We will come to the lake and assemble into 3 lab groups each time of 3 people each. If you really want some specific group of people, you know, I guess I'm just going to say, okay, every group needs a chair. Who's going to be a chair? Every group needs an equipment manager. Okay, please assemble 3 groups. So you could just be prepared for that's how lab will start. I will demonstrate the lab equipment. I'll say, here's the safety rope. Not that we'll need it, but you know, there's the safety rope. Here is the measuring tape, the surveyor's line with which you will measure the lake. Here's the GPS unit for getting the UTM coordinates, which is not essential, but it'd be good if we could work this in and actually use this. And then I'm thinking, I'm simply, in my mind, you know, I'll give you like maybe some additional instructions when we get to the lake, and I'll say, okay, we're going to keep it simple today. Just do this. So if you're going to be the chair of a group, be prepared. Read everybody should, but read the lab handout carefully so you know what the lab is, and then be prepared to listen for verbal modification. I may say, to keep this simple, we're going to do this. Equipment managers, you know, be prepared to get some instructions. I'm going to say, hold it like this, press this button to turn it on, wait, press this, read this. right? I don't know what else I need to say. Do you have any questions? Didn't do that hydrology thing. It's a really short thing, but so we will have to do that next week. I hope you liked seeing those lakes in Minnesota. I spent far too long putting those little pictures into that PowerPoint. It's just silly, but I've always wanted to do that, so I did it this time. Questions? Is everything clear? If everything's clear, give me a thumbs up so that I know. Can you do that? Everything clear? Oh, good, good. Oh, that makes me feel good. Okay. Oh, no. Abdul says no. Abdul, you got a question?
No, I just gotta watch this again to get it all down.
Okay.
Alright.
All right. So I will see everybody at Round Lake, just off Arcade and Frost in St. Paul on Thursday at either 1 o'clock or 2:30. And if you don't remember which, look on D2L to get your assigned time. It's perfect. We have exactly 18 students, so it's going to work out perfectly, like a jigsaw puzzle. All right, I will see you all on Thursday.
Thank you.
You got it.
Thank you.
Thanks for coming to class.